Thanks. Hi, so I'm Akshat Sharma. I'm a TME at Cisco Systems. Just to give you guys some context, I do deal with a lot of web customers as well as large-scale service providers. So some of the use cases that I will sort of speak about and then try and correlate to what I'm talking about, at least at the API layer, you'll sort of know what the context is in terms of where I'm pulling them out from. So let's sort of consider what we're really talking about in this case. What brings us here? This isn't a new paradigm altogether. I'm going to speak about what's been done in this space earlier and also what's sort of the pre-existing construction around what vendors have done as well as standards organizations around the network infrastructure layer. Before, of course, I set context on what this layer actually is. So let's see what actually brings us here. There have been plenty of standardization efforts in terms of at least trying to define what the network infrastructure layer is. And I'll give you context on what the different components sort of are at this particular layer. But just to start off, the Network Processing Forum, if some of you guys are aware of what that was, I think in 2006 is when it probably merged with the OIF. But they took the first stab at creating APIs at the network infrastructure layer. So think about APIs around RIB, around the label switch database, the APIs on the interfaces, notifications, etc. So some of the links that I've provided here would be good to take a look at to see what was actually done around the 2003-2004 timeframe. But in addition to that, I2RS is probably the current ongoing standardization effort around this space. We have a lot of focus primarily on the RIB and the label switch database APIs. I think less so on the kind of transport that ought to be used for that to be actually useful, specifically for controllers or your own protocols that you might want to run on your devices. However, this is an ongoing effort, and it sort of speaks about specifically the model-driven aspect of what this API must look like. And as you might imagine, being at the ITF, Yang is the preferred modeling language in this case. But in both of these cases, these are sort of standardized efforts, and yes, people have put in a lot of effort over time to be able to define what this layer needs to look like, what the APIs need to look like. But over time, what we've really seen is that network operators have sort of taken it upon themselves to be able to leverage whatever they know about network protocols and how they implement it using their own custom logic and try to bring it within their operational sort of paradigm. And we've really seen most network operators, specifically in the large-scale web service providers, implement their own routing protocols or their own controllers that help sort of facilitate what they would want to be able to do over and above typical routing protocol influence on the network. So in a way, over the last few years, we've seen a really strong effort to be able to make sure that most vendors expose this particular layer, the lowest layer within the stack, to the end user. And to set the context right, let's consider where these APIs actually sit. I'm going to break down the overall network stack into some relevant pieces for most people in the audience, but I'll also talk about what they naturally represent. So this is a typical representation of how you would break down a network stack. So you've got right at the top, you have the management layer. So you expect CLI, SNMP, telemetry, syslog, all of these different interaction points exist at the management layer. And they're really just abstracting what the device or the vendor device or general Linux device can potentially expose to you directly at the management layer. But in addition to that, right below the management layer is where you have the crux of the protocols and the features that you might expect within the network stack, right? So when you consider BGP or ISIS or OSPF, etc., they're really just existing at the application protocol stack layer, and the logic gets implemented there. And we'll sort of talk about the APIs at every layer, but I'll just break down the stack first. And right below the application layer is where we see the network infrastructure layer, so to say. There are other names for it. We tend to call it the service adaptation layer, but either way, they sort of refer to the same thing. The components that I would normally look at this particular layer are generally RIB, the label manager, BFD, interfaces, and a bunch of other lower infrastructure components, even L2 for that matter. One of the layers that I do not show in this case, right above what you would expect the ASIC SDK, is typically based on the implementations of different vendors. You might have either HAL layers or any sort of abstraction, let's say even the P4 runtime that allows you direct programmatic access to the forwarding entries in the stack. I gave a small snippet of course, what each of these layers represent. But let's try and consider what the challenges are with respect to the APIs at different layers before we come to the network infrastructure layer. So when we consider the management layer, this is the most typical layer all of us interact with. We are in the process of making sure that we have modeled APIs for everything at the management layer, which is a good thing. However, it is primarily a transactional exercise from the perspective of the programmer. You're trying to make sure that the router or the switch behaves in the way that the features that have been coded into it are expected to behave, right? So the API is basically just a hook into making sure that the features behave the way they should. And that's what the manageability layer primarily does. But in addition to that, if you look at the application protocol stack, this is where it sort of gets interesting. A lot of vendors at least do not expose this particular layer as an API, at least not yet. However, of course, when you consider most of the open source protocol stacks, GoBGP is a clear example. You've got an API on top of it, which allows you to interact with its state machine, at least in parts. And the crucial aspect there is that this is a pretty good layer to be able to help interact and influence the routing in your network. However, as I mentioned, in the end, whenever you're programming a network device, it is a transaction exercise. So you have sort of a request-response formulation in terms of how you're dealing with the device. So let's assume that your primary injection point is BGP, right? And in such a context, it's absolutely fine to be able to depend on the BGP stack to be able to finally inject the path that you need in the network. The only consideration here is that there is no ACK as such from that protocol layer trying to tell you whether or not the RIB or FIB has been programmed in the way that you need. So you would typically set up maybe a telemetry service from RIB or FIB combined with the transaction that you do on top of BGP to be able to have a complete system that works. And in addition to that, bear in mind that once you're dealing with protocol APIs, you're dealing with the semantics of the protocol, right? So if you're dealing with BGP, your controller or your applications would have to have context of either the NLRIs that you're using or the path selection algorithms that might affect how the path gets downloaded into the RIB. So there is some amount of complexity involved in how you would deal with the higher layer. Skipping the network infrastructure layer, let me quickly talk about the forwarding entry layer, which would exist underneath that. This is also a very typical sort of injection point for forwarding entries. OpenFlow, P4, especially with the P4 runtime service, are examples of how you would have sort of programmatic access to that layer. The only aspect with respect to the forwarding entry layer is that in the end, you have to have context of what the routing table state of the device is in order to make sure that multiple entities trying to program the forwarding entries can have the correct conflict resolution, right? So as an example, if you have a controller and it wants to be able to inject a path, but that next hop is resolvable, say, through an IGP, then you need to be able to make sure that whenever the IGP removes that next hop, you're able to get that state notification back into your controller so that it knows exactly how to handle the next set of steps, right? So there is a lot of information sharing that needs to happen between multiple entities trying to program the forwarding entries. So there is some complexity involved, specifically when you start dealing with multiple agents on the system. So that brings us to the network infrastructure layer. to me, this seems like sort of a balancing point between the two layers that I just spoke about. You get conflict resolution out of the box because, of course, you have the RIB to work with, and I'm talking about primarily about the path injection algorithms at this point. So having multiple entities is not really a problem. You have admin distance as a tool to be able to do the conflict resolution, even if you have multiple protocols engaging at the same time. And in addition to that, even if you compare to the application protocol stacks, at this layer, you do not have the complexity of the state machine that protocols might bring in, right? So in a way, it's slightly simpler to work with this particular layer, and you get the conflict resolution capability. So it is definitely a layer that becomes super useful for most programmers trying to operationalize their network. So this is effectively what we're talking about, right? We are trying to effectively create a bridge between the application layer and the hardware. And we want to be able to do it in a way that we provide conflict resolution out of the box and simplify the state machine that you have to deal with. All right, so use cases. Let me sort of jump through some of the use cases one by one. Some of these use cases would be pretty obvious to folks who have dealt with specifically the CDN providers who've dealt with TCAM optimization on their boxes. In this case, programmable route downloads, I don't know if the Fastly guys are here, but they specifically wrote an article maybe a couple of years back that went into how they use BERT to be able to influence eventually the programmatic access into the router. So I'm just sort of inspired by that same use case, but I'm talking about it in a slightly different light. However, think about CDN POPs where you have few host machines and typically a single router that these host machines connect to. So TCAM optimization in general is top of mind for most of the CDN POP providers, and they want to be able to make sure that the number of routes they actually download into the box is something that they control based on their logic. And here's an example where, let's say I have a BGP stack that might be running either on box or off box, and it could pair with external providers or with the other host machines within the system to be able to then pair with a controller agent, which then manipulates the routes and pushes the selective routes in. You could also have the BGP stack directly pair with the BGP stack on the router and try to inject the routes directly that way. So there are different ways in which you could do this, but think of the device to host ratio as a primary driving point in terms of why you would want to do this. Cost is a primary driving factor in this use case. In addition to that, I think traffic engineering and path selection is pretty obvious. You want to be able to make sure that the application traffic that gets sent across your network is able to influence how the routing happens on the network. So typical expectation here is that your label to prefix mappings would be taken care of by the controller on demand, assuming that the controller has access to the application workloads running on the data center. So usually a combination of this is good to be able to make sure that you have the right path constantly maneuvering based on the application traffic changes in the network. And bringing your own protocol or agent, right? So we've only spoken about controllers in the previous two use cases, but there are a number of relevant use cases around people trying to bring their own protocol or own agent that runs on the box in a distributed form factor and does pretty much the same thing, right? So as an example, let's assume that you have a typical IGP, and you want to be able to influence how the information gets distributed in between the different routers through TLVs that you want to add to the routing protocol. Now, you might not want to typically, get that TLV standardized, wait for the TLV to be standardized within the standardization forums, or even get vendors to necessarily implement them. You want it now. Right? And in that context, being able to bring that agent or protocol and run it on the boxes, making sure that they're able to communicate while still making sure that they interact with other potential protocols on the box with the correct conflict resolution, that's a use case that a lot of these web service providers have been dealing with. So I did mention earlier that when you have multiple acting agents on the system, conflict resolution is a problem. You want to be able to reduce that complexity. So having access to the network infrastructure layer is sort of key in that respect. So yeah, so we've basically covered 3 use cases, right? We've spoken about how we could potentially do TCAM optimization based on how we do route downloads into boxes. If you have access to the label switch database, you want to be able to do traffic engineering and path selection. And if you have your own protocol agents, then you do pretty much the same thing, except in a distributed form factor. So it all depends on the use cases that you're going with. So how do we actually build this API layer? I think there is some prior art to how these APIs have been built in the past, and I'll refer to them towards the end of the presentation. However, let's try and build this API layer from scratch. Right? There are certain requirements around how we might want to meet certain requirements at this layer. One of the major tasks here is to make sure that the API is super performant. What you're really trying to do is try and supplement the capabilities on the box by potentially bringing your own protocol, right? Now, if you bring your own protocol and you want to be able to compare the performance of that protocol with whatever is already running on the box, you have the disadvantage of being disconnected from the internal APIs that the, let's say, the vendor protocols have access to, right? So internally, the BGP, ISIS, OSPF stacks in a typical network OS implemented in C would have C APIs to talk to the RIB and the LSD and so on. You may or may not have access to that based on the devices you're working with. So performance is definitely a key here. Either we could introduce the API directly as in the same exact language that it is implemented in the box. Then, of course, you have to implement the protocol on the box in exactly the same language, so that becomes a constraint, and we'll sort of get into that. But the primary requirement is to make sure that you have a way of either running on box or off box and be able to do that in a performant manner. And we'll address that in just a bit. And what you really want is an API for the do-it-yourself system, right? You want a system where you might have certain components from the vendor, certain components from the general community, certain components from your own repertoire, and you want to be able to combine them to bring your own system together. So you want an API that allows you to do everything that a normal protocol would, but nothing more, right? You want the API to basically just be at the lower layer and not try and give you more than what you would really need with your own protocols. And offloading low-level tasks is kind of obvious when I spoke about considerations around what the network infrastructure layer can bring, specifically around the conflict resolution aspect. So, and scalability as well, right? So if you want to be able to implement, let's say, a path injection algorithm, you might not necessarily want to actually implement the scalability that a RIB should bring in, along with the conflict resolution capabilities that a RIB should have. So allowing the network OS to handle the RIB functionality for you, while you concentrate primarily on the higher level functions, is something that becomes super useful and reduces your complexity in the end. So giving you context again, we need highly performant APIs, right? So batch updates to the RIB, to the label switch database, and a lot more in the future, hopefully, will be something that we want to look at. Controllers and or vendor open source protocol stacks are pretty much in the same realm with respect to how they interact with this layer. You would typically expect direct access to the label switch database as well as the RIB to be able to inject your entries. You would also expect actually notifications from the RIB. If routes get removed, you want notifications to come back to you so that you can recalculate what you need to do. In addition to that, BFD and interface notifications are kind of obvious. This is how a typical protocol stack on the box would actually expect these APIs to work, right? You need the notifications from systems that allow you to recalculate, and you need performant access to the components that allow you to inject the routes or the label prefix mappings as you need. So yeah, streaming notifications from BFD events and interface events is a key component of how these protocol stacks would work. In addition to that, I mentioned API for the do-it-yourself system, right? So you're bringing your own protocol. The network stack really needs to provide you only what you need. If I'm bringing my own BGP stack or if I'm bringing my own controller, I don't necessarily need to go through a bunch of features exposed in between the network infrastructure layer and my controller. I really just want access directly to the network infrastructure layer. Give me the performance, give me the API on top of it, and let me do what I need. Don't give me anything more than that, right? So this being able to implement an API that is structured such that the access basically defines what the network infrastructure layer is supposed to do is allows you to make sure you can concentrate on your high-level functions and still just deal with potential issues only at the network infrastructure layer and not with features you don't need. In addition to that, being able to offload functionality was the last aspect. Conflict resolution and scalability are concerns. So if you're able to let the network infrastructure handle that for you, you can really concentrate on what your controller or protocol is actually supposed to do. You do not need to manage synchronization between multiple agents on the system. You also do not need to manage how these systems would scale out when multiple entities are programming the same RIB data structure. So in a way, being able to offload these characteristics to the network stack really reduces the complexity that you would have to deal with at the higher layer. So let's tie all of that together. Think about these three primary requirements, and we're going to hark back to them as we go along. All right, so let's start building these APIs for the network infrastructure layer. We're going to meet performance requirements, potential exhaustive APIs around the lower layer requirements, as well as the offload requirements for these APIs. So it's tough to generally summarize if this would meet all of the requirements around an API at this layer. However, at least based on some of the experience that we've had internally as well as with some of our customers, I think this is pretty much a given. If you meet these three requirements, then you're trying to basically build an API that's actually useful. So when you consider model-driven requirements, I think there is no question that if an API is created in this day and age, it needs to be model-driven. You need to have version contracts of what your API can do, and your documentation as well as your capabilities flow from that version contracts. So in this case, multiple options for this, of course, because we have a lot of things going on in the community. Protobuf ideals is one way to go with it, specifically if you're going to use gRPC as a transport mechanism. And Yang, of course, is something that you guys would realize from the I2RS context, irrespective of the modeling language that you use, in the end, it needs to be compatible with the transport layer that you select to get the highest performance. So the second aspect is the remote procedure call, the RPC support. I think I mentioned earlier that, yes, we could expose the exact same API in the same exact language that the network OS is implemented in, so that you can bring your own agent and make it sit on the box and use the same API. And that will give you a lot of performance. But of course, you're constrained to running that agent only on the box, right? If you want to be able to write it in the language of your choice, if you want to be able to push it out of the box so that you can interact with multiple boxes at the same time, then you're stuck with either dealing with abstractions on top of agents running on every box, or you have to create your own abstraction layer at a higher layer for language agnostic requirements. So RPC support is also a given. gRPC thrift are powerful RPC examples in this context. I did mention earlier that performance is a key requirement. So being able to use something like gRPC gives us a lot of the performance requirements at this layer. I've mentioned that a lot of the standardization efforts haven't actually looked at potential transport RPC mechanisms necessarily. So this is probably something that needs to be considered. If you're bringing your own controller or protocol, you need that performance channel to exist. So gRPC or thrift RPC would be ideal combined with the model-driven contracts that we've already spoken about. Finally, a layered approach to these APIs. I did mention earlier that in the end, you want the network infrastructure at the lower layer to give you only what you need. No need for features that you don't need. Be able to work with the components that these APIs expose. But these APIs also need to be exhaustive, right? So if these APIs cover everything that the network infrastructure layer can provide, then you have a pretty complete way of bringing your controllers and protocols within the operational space. All right, so where is the code? I'm going to refer to a few of the vendor examples of what we have. Since I'm from Cisco, I'll have to give you some context on the Cisco API because I don't have enough context on the other vendors, but there will be references to how the other vendors do it as well. So in this case, let's look at where each of the vendors are. Cisco has a bunch of service layer APIs that they're exposing on the iOS XR stack. You'd want to be able to take a look at some of the GitHub repositories here, as well as the XR docs links that indicate how to actually use this API. These are Doxygen-generated documentation, so hopefully they remain pretty much in sync with the proto files that are published. Now, how are these APIs actually implemented? This is what the iOS XR stack does. So you have a gRPC server running on the router, and you basically use gRPC as your protocol that you want to be able to communicate for RPC requirements. In addition to that, the protobuf ideals are used to define some of the basic functionalities around the infrastructure layer. Now, I mentioned some of the requirements around infrastructure layer are focused on the four main paradigms, which is getting some sort of RIB RPCs, MPLS RPCs, combined with the interface and BFD RPCs for notifications. So splitting up all of these requirements into these different functionality domains basically allows you to version them on their own and bring new functionalities in each one of them as needed. But the primary requirement is that once you've divided up each of these functionality domains, each one of them needs to be complete in its own respect so that you have full access to the RIB or the label switch database in the same way that a protocol running natively in the vendor stack would have. So yeah, and of course, the biggest advantage of using the RPCs is something like gRPC. You get a lot of language agnostic behavior. So create your own Python, C++, or Golang clients, and you should be able to talk to the device. Further, if you look further into what the API should really do, there are different aspects here. Within each functionality domain, you need to have certain basic RPCs that have to be covered. One of the main ones that I'd like you guys to think about is the op RPC. The op RPC needs to be CRUD-based, of course, and that CRUD-based operation allows you to create, delete, update objects as needed, and that is pretty much what you're going to work with in a manner similar to other stacks on the box. In addition to that, you will notice some of the other pieces are pretty obvious when you start connecting to the box over the RPC. You need to be able to have get-stats APIs to extract information on what the particular domain has in terms of capabilities on the box that you're dealing with. And in addition to that, to have sort of streaming and notification variants of those get APIs so that if you are working with a controller or an agent that deals with streaming notifications, you can work with that as well. Now, further, there are different ways in which you could potentially implement this. You could have a completely synchronous RPC, which basically connects to the box every time you have to do something, and netconf comes to mind in that respect. But what you would typically do in this case is maintain a channel that connects to the box for a while, and because you can multiplex multiple channels within the given RPC, you can basically send other requests around RIB, MPLS, etc. on top of the existing channel. And that gives you a way of both getting high performance, but at the same time, maintaining a channel that allows both the server as well as the client to know when the client is connected, right? So there is a lot of synchronization efforts that come in if you maintain an initialization channel in this respect. So that sort of covers what the iOS XR API stack is doing at this particular layer. And in addition to that, we have the other vendors. They have APIs in pretty much the same context. This is pretty much what I could glean from the documentation that exists at this point. The Juniper extension toolkit, Jet, sort of covers these APIs over gRPC as well. So they are pretty much doing it in exactly the same format. And you do get access to the RIB, MPLS, and interface components. So the network infrastructure layer is pretty much implemented in a similar fashion. So it's a good thing that most vendors are looking at things like gRPC and Thrift as capable RPCs for working with this particular layer, specifically for the performance. The Arista EOS SDK has existed for a while. It is probably the more mature one because it's been out for a while. It is, however, a C-based API and it is not model-driven. I wouldn't suppose that would take too long to change. However, at least from the perspective of getting access and having a slightly mature API, they're already there. So that's a good thing. But yeah, in terms of meeting all of the requirements that I spoke about earlier, you would really want a model-driven API that works over an RPC to solve most of your on-box and off-box client requirements. All right, so let's look at a quick demo. I would typically do a live demo, but I was asked to mitigate all the risks possible. So there is a video that I'll walk through. I did do it yesterday, so it was close enough to the presentation. Hopefully that counts as a live one. So programmable BGP route download. This is a use case that is again inspired from the CDN use case I spoke about earlier. Some of you, if you were at the Beer and Gear yesterday, you would have seen this demo already. So yes, it does work. And I'd like to be able to address exactly what are the benefits that you're getting because of that API existing at the network infrastructure layer for you to be able to solve these use cases. So let's look at a couple of routers. Oh, by the way, just for context, we actually implemented a part of this code in the last hackathon at NANOG. So most of this concept comes from the conversations we've had at hackathons right here at NANOG. So in this case, we want to be able to emulate the CDN use case and the BGP session that exists between router 1 and router 2 that you see here. It could be eBGP, IBGP, it doesn't really matter. In this case, I have just selected IBGP as a use case to be able to differentiate with another eBGP peer that I will show you in the demo. But effectively, the purpose here is that router 2 is the one that's going to inject routes into router 1. And on router 1, I have a single route policy that says drop all the routes because I don't want the BGP stack to manipulate the RIB for me. What this basically does is, except for the adjacency in RIB of BGP, none of the other RIBs are evaluated, right? So the adjacency in RIB still goes over BMP to the OpenBMP collector. And when you do a show IP BGP on the router, you would see nothing. So no routes from router 2 are actually getting installed or are being manipulated by the BGP stack on the box. However, that doesn't mean that the BGP stack is not doing anything because, yes, it is forming the neighbor relationships as well as getting the route updates and redistributing them. So we're not trying to extract the protocol functionality out of the BGP stack. We're really just extracting the RIB handling more as a large data set problem rather than a protocol problem. The only protocol as such that is involved is the BMP protocol. And the good part is that it gives us all of the hooks that we need to be able to manipulate the routes coming in with respect to our requirements, the route policies that we want to bring in, path selection algorithms that we want to bring in, and then condense those routes coming in into the final sort of local RIB that BGP normally creates before you push it onto the router. In this case, the whole point of that gRPC-based connection that you have between the controller and the router is to give you enough performance so that the entire system, which is the controller plus the router, can actually behave as a single logical entity and can somewhat represent how a single BGP stack would behave. It is, in a way, impossible to attain the performance of a native BGP stack. However, you can get as close as possible so that at least your use case is met. So it depends on your use cases. I wouldn't recommend running this in production for any of the typical path convergence requirements. But specifically, if you're looking at selective route downloads and your own utilities around path selection and route policies, you would want to be able to work with something like this. So there are three aspects that I'd like to be able to cover here. One is, of course, the performance because of the channel that you get if you have a gRPC or a thrift RPC in between. In addition to that, the flexibility, so once we've extracted the RIB into the controller, you get your own route policies and own path selection algorithms to do what you want with the RIB, right? You can reduce it as much as you want. You can have silly little conditions that just say that I want the second subnet to be 2 or something. And you can combine all of these different factors to determine what your final local RIB is going to be. In addition to that, the offload aspect, and remember, I'm really just tying this all to the initial requirements around how this API must be implemented. So we're offloading capabilities of specifically getting the route updates and distributing the routes, etc. We're letting BGP on the router do all of that, right? We're not building a protocol in this case. We're simply leveraging the network infrastructure layer API to be able to exist alongside a typical BGP stack, right? So this gives us the opportunity to look at the system as if we are just another entity on the system, right? I could have as many protocols or controllers sitting on the system. The conflict resolution takes care of the problems for me. All right, so let's look at the demo. It's the first time I'm doing a recorded demo, so I'll try and time myself. Okay, so top two windows are controller on the left-hand side, which is the one that's going to get routes from the Kafka bus from OpenBMP. And top right is the, in this case, the service layer API client for iOS XR that's going to actually push routes in. At the bottom, you've got two iOS XR instances that are peering over IBGP. Router 2 is on the right-hand side, and that's the one that's going to inject routes into router 1. So what I'm doing here is showing you a show BGP summary. I don't know how many of you can see it properly, but I have two neighbors there. One is 2222, which is router 2. That is peering over IBGP, but at the same time, specifically the prefixes, if you see that, I get no prefixes from this particular router. The other one is a Quagga instance that is actually peering over eBGP, and from that I'm getting about 6 routes. So now, all of this is a function of the route policy that I should show you in just a bit. Now, on router 2, let's look at the running config. I did mention that I'm sending a bunch of routes over the IBGP session, and they technically should be accepted and installed on router 1, but they're not, primarily because when I do a show run router BGP or show IPBGP on this guy, you will see that I don't see any routes from this particular router in the BGP routes. The only routes that are coming in are from 11.1.1.20, which is the eBGP neighbor that I'm peering with. Okay, so keep going. When I do a show running config here, I'll show you exactly what's happening. On the neighbor 2222, which is router 2, I have a single route policy that says quick start drop all the routes coming in. I don't want BGP handling these routes. And once that is done, what I should show you, hopefully, is the BMP setup at this point, which is used to get the adjacency in RIB data into the controller. I will run the controller in just a bit, but I do show you BMP. Yep. So when I do a show BGP BMP, it sort of indicates that I'm actually, for both the neighbors, I have a BMP session going. And some messages have already been sent across to the OpenBMP collector. And for neighbor 2222, that's the one that I'm interested in. Even though I'm dropping all of the routes and not manipulating them on the box, I'm still going to send them up to the OpenBMP collector. All right, so let's start the controller. There. So once the controller starts, it connects to the Kafka bus. It starts manipulating all of the routes that are coming in. And it does all of the normal BGP manipulation, right? Gets the adjacency in RIB, applies the route policies, gets the adjacency in RIB post policy, then applies path selection algorithms, gets the local RIB. And the local RIB, in the end, has no context of the BGP knobs, but all the RIBs before that have all the context. So if you want to manipulate local pref, med values, whatever else you want that BMP gives you, you have access to them because in the end, BMP is already streaming that data to you. In addition to that, I ran the service layer API client there. What it really did was get the local RIB that was also published over the Kafka bus and convert that into a batch update that goes into the router. So let's look at show route on router 1. And what you see now is all of the routes that we were sending from router 2 have actually been published into the RIB for router 1 as application routes. This is crucial to understand. We're basically mimicking a protocol, and that's exactly what's happening here. It's coexisting with the BGP stack on the box. It's coexisting with actually OSPF running on the box as well. And because of the conflict resolution you can afford as a result of the admin distance knobs that you have at the network infrastructure layer, they all coexist without me having to implement synchronization algorithms between the controller and protocols running on the box. I don't care. I'm just another protocol. And at this point, just to show you that the entire system actually behaves as a single entity, purely from a performance aspect. And there's a disclaimer here, this was written in Python, so I can't claim performance. However, once it is written in Golang, it will at least be 10 times faster. So the point here is that it acts as a single logical entity. So when you remove the routes from router 2, the routes that it's advertising, I'm going to wait for the BGP update cycle. And basically, what you will see is that these routes get pulled out. BMP gets that information again, creates a delete event for all of these different routes in the local RIB, which in turn triggers the service layer API client, which then goes ahead and creates a delete batch and removes the routes, right? So it's acting at the behest of the events happening on the network. In this case, route pull. So it just happened, and you just saw a delete success on this guy. So let's look at the routing table on router 1. There. So it's back to just BGP routes coming from the eBGP neighbor, nothing from router 2 again. We've now actually removed it. At this point, of course, I can go ahead and put those routes back in again, and you will see that the entire system continues to behave as a single entity. So the top 2 windows and the bottom left window are being treated as a single BGP stack, responding to all the events that are coming in. Think about the use cases around that. I mentioned earlier as well. You have the capability to bring your own route policies and as well as your path selection algorithms, but at the same time, you can do selective BGP route downloads. So if you want to optimize your TCAM space, that's one way to do it. Okay, same thing happened once I added the networks, and I had an update success in this case. That's purely based on the logic I've written in my abstraction. But once you go to a show route, you'll see those routes pop up again. All right, so that sort of completes the demo. And going forward, coming back to the use case itself, you get the performance because of the RPC that you have available. You get the flexibility because you're basically exposing the network infrastructure components to the end user. And by ensuring that the network infrastructure itself is not completely dumb and it has certain capabilities, specifically on conflict resolution and other stacks, you can offload characteristics of your controller or agent to the stack while you concentrate on what's actually important for your application use cases. And there are a lot of other use cases that we are working on. And I would suggest, of course, taking a look at the GitHub repo here, as well as the organization associated with it. And you'll find a lot of other pieces of code being thrown in around there. So yeah, that pretty much covers what I want to talk about. But seeing model-driven APIs at this layer would be, I think, ideal for a lot of the users in this space. All right, thank you.
Looks like you're off the hook on questions.
Yeah, all right. Thank you.
Not so fast. Hold on. Hold on.
Oh, we do. Oh, you
Come
have
back.
questions. Okay. Yeah. So we have time for maybe just one question.
Okay.
All right.
So you showed us the network prefixes that you originated from router 2, right?
Yeah.
Getting to the RIB. You didn't show us the BGP part. Do you still have the prefixes there?
No. So if you do a show IP BGP, I should have had my laptop, but if you do a show IP BGP, it'll have no routes in it.
Right. So, but BGP still needs to advertise those routes to the peers.
Correct.
So,
So the only RIB that you would manage on the BGP stack is the adjacency out RIB.
right.
Yeah.
So, which means that you still need to calculate a best path locally, or are you going to get that from the controller?
No, because the controller is doing the best path calculation and it is determining the local RIB and it's programming the global RIB for you. So the path selection is already done. At that point, it's basically about redistributing it into other protocols or to other routers on the system.
Right, right. But BGP needs to get that best path calculated from the controller, right?
It basically uses the global RIB and expects that if you redistribute the application routes, it'll just push those routes into whichever neighbor it's communicating with.
So you're redistributing from RIB back to BGP?
From the RIB back to BGP, yes. So it's
Have
only
you
one RIB.
Have you measured the performance of this?
I don't have the full performance measurements. As I mentioned, I want to be able to do that with a combination of Golang. But yeah, the performance is never going to be as great as a native BGP stack. It's basically about the flexibility that you get by taking it out.
Okay.
All right.